and look in the very first paragraph, you'll see that it basically says, computer programming language tries to have as few implementation dependencies as possible so that developers can write once and run anywhere. So anyone who was a software engineer in the late 90s is certainly familiar with this concept. And so I thought it'd be fun to maybe take a look back and see how this all worked out. I remember when I got a Java application with a GUI running in some CS course in the 90s, and I was super excited to actually see it working and in action. And clearly, the cool thing about it was that Java-based program could actually, I could run it on this Windows machine I might have been using, and then go put it on a Solaris box. We actually had Solaris desktops back at Cal Poly where I went. And it could run in both places, and that was pretty cool. But it actually turned out that people hated this because they want native experience with GUIs. We actually see that today with mobile phones, right? So, okay, this was cool. It proved that you can, in fact, write once and run anywhere, but actually not very useful, right? So let's kind of maybe figure out what the next way to use this technology is. So remember that Java the growth of Java coincided with the growth of the internet. So this chart kind of shows that in the late 90s to the mid 2000s, there was quite a rapid pace of growth of people using the internet, and this happens to coincide with the growth of people using Java, right? So this provided an interesting problem to solve with the write once, run anywhere concept. How do we deliver kind of rich content through the browser to the end users? And so applets were born, and obviously that was kind of neat also, but it was another kind of terrible moment in the history of Java because it just basically made, for a lot of ugly animations and whatnot. Actually, funnily enough, I was going to try to Google for examples of bad applets, and they've been erased from the memory of the internet. It was such a bad period in time, no one has them on, I couldn't find them. So anyway, that was also interesting, but again, not that useful. I think it's fair to say that Java really started to become popular when it proved itself to be a useful tool on the back end. And basically, I was in this situation in the early 2000s where, the Windows desktop was dominant. We all had them at work, but we were writing applications that would get deployed to, Solaris or other Unix-based operating systems. And so this was, again, neat, and it proved that you could write once and run anywhere. But this was also probably the first time it was very useful. So that's great. It really started to take hold on the back end. And the next step was to kind of formalize this back-end use of Java with something called Java EE, where basically we add a lot of core libraries, deployment formats. This is where the WOR file was born, or the infamous EAR file, which no one actually used. And this was great, right? So Java was really starting to show its strength. But ironically, what happened was that each vendor created its own app server, which required basically its own SDK. And sometimes you actually had to use their IDE. And so we kind of lost the whole principles of write once, run anywhere. You basically had to write once for just that version of an app server. So what happened next was that basically everyone fell back to the least common denominator, which was a servlet container. The Spring framework proved to be very useful because basically it adhered to those original principles. Let's adopt one SDK, write to it, and then universally applicable. So anyway, we've seen this story before. Write once, run anywhere. So let's see how much of this applies to where we're at in the big data ecosystem right now. A couple things have changed since that point in time. Probably the most important one is that vendor standards are not really what drives technology adoption anymore. Open source has proven to be the way that the community at large adopts new technology. And so whoever has the best open source project is going to win. Also, this is the era of big data. Data's kind of overwhelmed us, and as a consequence of that, distributed systems are the new standard, right? So this is great. Big data platforms are everywhere. Everyone's got a Hadoop system or maybe Cassandra or whatever. But the truth is that there's not a large ecosystem of quote-unquote big data applications. There's a whole lot of people who maybe have a little bit of ETL integration or connect through an ODBC or JDBC driver, but we haven't seen an ecosystem of actual apps, of big data applications. And I think the reason is that essentially it's too hard to do. There's so many different systems to piece together to actually write a full app. And on top of that, if you do try to piece together these different systems, the set of systems and interfaces you might use on one vendor distribution are completely different in terms of runtime and compile time versions from one platform to the other. It makes this very hard to do. So basically, each distribution has its own SDK, and we've kind of fallen back to exactly where the Java EE landscape was with the app server and the Java EE spec. So the big data ecosystem needs a common SDK, and of course, we at Databricks and in the Spark community believe that Apache Spark is the answer to this problem. You've seen charts, graphics like this quite a bit, and you've seen a lot of people talk about the libraries that are available in the Spark ecosystem, the user-friendly API, the fact that it's a full-featured programming environment, and these are all really important reasons to use Spark. But there's other solutions that do that too. What gets understated often is that by using this SDK, as I'm calling it here, you actually abstract yourself away from a lot of runtime dependencies. The framework takes care of those for you, and you can write once and run anywhere. In other words, write a Spark application, run it on several different Hadoop distributions without having to change your code at all. And this is a really key and important concept beyond just the useful features that are in the box, which are also outstanding. Let's talk about how applications are composed in Spark and see why this is possible. So basically, when you write a Spark application, you are kind of choosing whichever one of the programming languages that you're most comfortable in. Within that programming environment, let's say it's Scala or Python, you're pulling in libraries, pre-existing libraries that might be useful to the problem you're trying to solve. And then in interacting with Spark, you're calling Spark's public APIs. So Spark Context, RDDs of some sort, maybe some of these library-specific APIs. And in doing so, you let Spark take care of the access and scheduling of getting to the data. So you are using public APIs that Spark provides. Spark itself takes care of the data access. And so again, you're kind of abstracted away from what the specific physical location of data might be. If it's something like, let's say you're using a Hive metadata described data format. Or in general, basically, Spark provides abstracted APIs like accessing, I don't know, Parquet files and things along those lines. So in any case, Spark does the best it can to prevent you from having to understand the fact that, yes, you're accessing a text file, but it's actually an HDFS, and the partitions are spread out throughout the cluster or whatnot. Another really important abstraction is the fact that Spark actually works with several different cluster managers. And this is actually a really important point, because I think a lot of people who are new to Spark assume that you have to have some kind of Spark runtime at the point where you deploy your application. And that's not necessarily true. In fact, let's talk about how you deploy an app to Yarn, for example. So when you write your application, and it depends on Spark, you've compiled it, you've packaged it up, and you want to actually run this app against, let's say, Yarn. At that point in time, there does not have to be any Spark service running on that cluster. Okay, now this would change if you had something like Tachyon that you needed, let's say, but in general, in the most basic use case, you're essentially deploying a Java application out to the cluster. It knows how to talk to Yarn as far as getting the resources it needs, but there's no runtime dependencies. This is a really important point. And because of that, you can actually take that same exact application and deploy it to these other cluster managers as well. So this includes Mesos and Spark Standalone, which is, of course, part of the Spark project, but it's decoupled from the actual application you build. So keep this in mind. In fact, let's talk about Yarn a little bit more. You can take two different Spark applications which are running at the completely different versions. So let's say a Spark 1.0 application and a Spark 0.9.1 application, and those can both run on the same Yarn cluster, assuming that the Yarn support in the app is at the right version. They don't even know each other exist, and that's just fine. So this is an important concept to keep in mind. The runtime dependencies are abstracted away from the end user in Spark. So that is basically what this next slide reinforces. You can not worry about these specific things. Let Spark take care of those. Write once, run on any of these different managers against many different data sets. So let's talk a little bit about how Spark handles the Hadoop dependencies. when it's time to compile Spark, you have to identify which version you might use. So of course, keep in mind, this is for someone who actually needs to compile Spark. And the nice thing about having all these vendors who are now providing Spark in their distribution is that most of you will never have to do this. So this is just kind of for information purposes. You're most likely going to use the Spark that's already included in the distribution, the Hadoop distribution, or let's say it's DataStax Enterprise or whatever it might be. You don't have to worry about this in most cases. But for the sake of understanding how it works, let's talk about it. So basically, at the time that Spark itself is compiled, you'd identify which Hadoop client you want to embed in the Spark runtime, and that Hadoop client becomes part of that binary. But like I said, in most cases, you won't even have to worry about this. Now, that's not to say it's hard to do. It's pretty easy. But nonetheless, if you have a distribution that's already got this Spark binary available, just use it. Makes your life easier. You can just focus on developing your application. And these logos here might not be the exhaustive list, but those are the ones who Databricks has partnered with or who have certified their Spark distribution. And again, you should be able to write once and run anywhere on any of these different platforms. And so this becomes a very ideal SDK to use if you're an independent software vendor or whoever. In Spark 1.0, a couple important features were added to make this even easier. So before 1.0, at the time when you wanted to actually submit your application to the cluster, so if you think back to a few slides ago where the point where you want to, you've packaged your application into, let's say, a jar, and you want to say, okay, let's go send this thing out to Yarn, use those resources, process that data, et cetera. Or maybe send it to the Spark standalone cluster. The process of actually submitting your application in the past was a little bit harder because it differed quite a bit depending on which cluster manager you were using. So if you wanted to submit to a Yarn cluster, it looked a lot different than what it would look like if you wanted to submit to a Spark standalone cluster, et cetera. With 1.0, there's a new feature that's part of the distribution that's built called Spark Submit. So you would go into the to the folder or to the directory, the bin directory of whatever distribution you're using. You call Spark Submit, you point it to your jar file, and it goes ahead and sends it out to the cluster. So let me actually show you how that works right here. So I've got this application here, very simple. Basically, this is, in fact, this is actually on the Spark documentation page. Oh, I'm sorry. Thanks for the heads up there. Okay, you guys can see that now, I hope. So this is a very simple Spark application. This is about as basic as you can get. You'll find this example actually on the Spark's website, on the kind of quick start page, I think is where that is. And you also actually, if you're going to training tomorrow, you're going to see this exact application is in the training USB that we're going to use. So anyhow, all we're really doing here is finding a file. Where's my cursor there? Finding a file. We're going to set up our Spark context. We're going to read the file in and just do a kind of a simple filter and count. Okay? So that's pretty simple. So the process of actually building this application, let me go show you what it looks like. You'll see that there's this is an SBT project. So one other important point to note is that Spark supports, well, actually, this is not necessarily a Spark thing because we're only depending on Spark. But in the Spark ecosystem and in the project, there's both SBT and Maven builds. So you often see people using SBT because we're very familiar with it, Scala developers and whatnot. So in this case, I'm going to use SBT as well. And I just showed you the source code. The other important part of this project would be the actual build definition. So you can see basically I've got a dependency on Spark core at 1.0. So if you were doing a project that's based on Maven, very similar concept. You just add your dependency to Spark. This adds the resolver here, which is another repo that we might need to bring packages in from. And based on this build file, I'm going to actually build this project. So this should be pretty quick, I hope, since I already did it before and all the dependencies are available on my box, on my laptop. Okay, that's done. So now I'm going to go into my Spark distribution. So again, whatever distribution you're using, pick your favorite vendor or whatnot, will have this Spark submit script in it. So it's in the bin folder here, right? Okay. And the way we call this program is to identify the class. What was it? Simple app. Identify the cluster. Sorry, I'm going to cheat here. So in this case, I'm just submitting it to my local cluster. Basically, it's not a cluster. One of the cool things about Spark, in fact, is that you can, whether you're using the shell or in this case, running a full application, you can just use the, it will launch kind of an ad hoc process that runs the Spark code locally using local threads as if it's running on a cluster. Exact same APIs and whatnot. Very easy to do. Okay, and then last thing I'm going to do here is actually go back and find that file that I built. So it was in demo app, target, Scala 210, simple project, and there you go. So you can see I got the result here. Lines with A are 73 and lines with B are 35. So that's a pretty silly little demo, but the point being that that exact same process that I used there is what I would use, well, sometimes a slight variation, but more or less the same script would be what I would use to submit to other cluster managers. So you can see in this particular example, I show you how to, the two ones that I copied, again, from the configurations, are how to do it against a standalone cluster. So essentially, instead of the master being local, in this case, it uses a Spark URI. And then in the second example, instead of using a URI, it says the master is yarn-cluster, which basically means use the local yarn configuration to submit your application to understand where the resource manager is and whatnot. Okay, so Spark Submit was, like I said, a really important way for us to kind of unify the different ways to submit jobs. This is new as of Spark 1.0 and very key to that concept, write once, run anywhere. Another important feature is Spark SQL. And actually, the thing about Spark SQL is when we decided what to name it, we actually struggled with whether Spark SQL was the right name for an important reason, because Spark SQL is not just about the SQL interface. So keep in mind, one of the most important things about Spark SQL are actually the schema RDDs that underlie the system. So with schema RDDs, oh, sorry about that. Okay, got it. So in addition to providing a new developer interface where you can actually write SQL, the way to actually implement the system that understands that SQL is with something called, well, with an optimizer named Catalyst, so that's important, but also schema RDDs, which is basically a way for Spark to natively understand your structured data now. So prior to Spark SQL coming into the system, you'll note that a lot of the examples you might see involve, as the first few steps, kind of parsing out fields by splitting commas and then picking like the fifth value of an array, let's say, and then starting to filter based on that. With Spark SQL, you can essentially, as you can see here, using the DSL, you can have the system understand a little bit about the data. And then in the case of this DSL here, you can see the people, the RDD of people, of person objects. So we've set up some structured data. We've set up a class named person. It obviously has fields in it. And then by creating a schema RDD, we can do things like refer to a specific field. In this case, we have the tick age, right? So typically, like I said, in the past, that would be like the fifth element of an array. In this case, we can actually refer to it by name. So we have the age field here, we have the name field on the end, et cetera. So anyway, point being that with Spark SQL, in addition to providing SQL language for a developer, you can also start to describe structured data And this actually abstracts people yet again from having to know specific things about maybe where data is stored or how to get to it. Maybe you provide a level of indirection by using the Hive version of Spark SQL, which understands how to access data through SERDES and whatnot. But to the app developer, you don't have to worry about all those mechanics. So that's another important way that this allows developers to, again, write once and run anywhere. So anyhow, last closing points would be that Databricks is committed to growing the developer ecosystem for Apache Spark. So for a lot of reasons, we think that this is the ideal big data SDK. And one of the things that a community needs to make an SDK successful are a lot of resources. So look out for us to provide a lot more training classes, online materials like videos. Basically, all the training that we're going to be doing should be open source and free to access. So keep an eye out for that. You can count on us to be committed to open source in order to, again, develop this ecosystem. And a quick note about our certification programs, which Jan announced yesterday in his keynote. Basically, the reason we did that is to try to discourage people from forking the Spark that they include in their distribution. So again, if this is successful, it should allow people to write once and run on any of those platforms. And a closing note is that Databricks is hiring, so please check out the databricks.com About Us page. You'll see how to apply for jobs at our company. We're looking for all kinds of folks to join, evangelists, trainers, solutions architects, software engineers, et cetera. So go out there and please apply. Thanks a lot. Are there any questions? Go ahead. Yeah, so the question was, in one of the slides, I had a little asterisk next to HDFS. HDFS, so HDFS, the file system as far as a place to store data, obviously Spark understands that. But in addition to that, you can do some pretty complex or more complex access than just grabbing text files, right? You can use like Hadoop input formats and get at some more kind of complicated data, I guess. Question? Yes. So the question was, what is the overhead when you want to use Yarn? So there might be some scheduling overhead in terms of Yarn actually providing the resources that you ask for. That's typically the one way that you might notice the difference between using Yarn and a Spark standalone cluster. But once the resources are granted to you, Spark stands up executor JVMs just like with all the other resource managers. And from that point forward, it's really no different. Any other questions? All right, well, thanks again. That was a little bit.